Let's evaluate this integral. So when I first look at this, the first thing that catches my eye is the square root term. And I'll spoil this for you, it does involve some trig substitution. And we've previously seen something in the form of a squared minus x squared or a squared plus x squared, but we haven't really seen something in the form of the square root of x squared minus a squared. In this case, we would want to use the substitution x is equal to a secant theta. And this comes from the trigonometric identity where tan squared theta is equal to secant squared theta minus 1. If it isn't clear why we're using this substitution for this question in general, or this question specifically, let's multiply this whole thing by 4. So then I'd have 4 tan squared theta is equal to 4 secant squared theta minus 4. And that looks very similar to what I have in this integral, and it makes sense why I would substitute x is equal to a secant theta, or in this case, x is equal to 2 secant theta. So now that we've established that that's what our substitution is going to be, let's find our dx term. dx would just be the derivative of 2 secant theta, which is just 2 secant theta tan theta d theta. Now that I have my terms all defined, I can rewrite my integral. So I have, let me go ahead and write my dx, or in terms of theta. So I'd have 2 secant theta tan theta over x squared, which is just 4 secant squared theta, and in my integral, does not have to be that big, is just based on the identity 4 tan squared theta. Don't forget the d theta outside. There's a lot I can simplify here. First, I can get rid of one of the secants in the denominator by getting rid of the one in the numerator, and my 2 in the numerator will simplify the 4 in the denominator, and I know I could get rid of the square root in the bottom, so I can rewrite my integral in a more simplified way. I'd have tan theta in the numerator, and then I'd have 1 secant. I have a 1/2 outside, and then I said I can get rid of my square root, so I'd have 2 tan theta. My d theta is still there, and I can see that I can get rid of my tan terms, and then I can also move this 2 outside, so my integral now looks like 1 over, okay, it seems like I changed the color. Anyways, 1/4 integral of 1 over secant theta d theta. Now, this is something that's really satisfying in my opinion. This can very simply reduce to 1/4 integral of cosine theta d theta. So we start in a really weird and complicated form, but we end up with a pretty simple integral. The integral of cosine theta is just equal to 1/4 sine theta, plus my arbitrary constant c. Now, as simple as that was, we're not quite done yet. Remember that my original integral is in terms of x, but what I have right here is in terms of theta. So I have to go back and make sure that everything is in terms of x. So remember, my substitution was x is equal to 2 secant theta. Isolating secant, it's equal to x over 2. Let's make a triangle out of this. If this is my angle theta, and secant theta is equal to x over 2, using my knowledge that secant is equal to 1 over cosine, and cosine is equal to the adjacent over the hypotenuse side of a triangle, secant is just that flipped. So I know that my hypotenuse is going to be x, and my adjacent side is going to be 2. That means that my missing side, which is the opposite side, is going to be x squared minus 4, or 2 squared. So x squared minus 4. All I have to do now is use my definition of sine to write the final answer. So 1/4 times sine is obviously equal to the opposite over the hypotenuse. So it's x squared minus 4 over x plus the arbitrary constant c. And that's it.